Hello and welcome to today's session of the Design for FDM Technology webinar series. It's a pleasure to have you all here with us. Thank you for joining. As we began last week, we tried to be short and precise to deliver a good overview over the topic of designing for FDM technology. While we also learned last week that AM and 3D printing unleashes creativity and you can do a whole lot, there are a couple of these restrictions and pitfalls that we'd like to make you aware of, and we'll share some best practices. As a reminder, we're going to have 3 sessions. Last week, we started already with the basics, or as I would call them, the fundamentals. You can find the recording online. You can find it on the Stratasys Academy. Just look for the handout. You can see, download the PDF, and feel free to register if you haven't done so already. Today, we're going to talk about some design considerations. And next week, we're going to look at some other cool features of advanced FDM. But again, who's actually talking? My name is Stefan Schuster. You see me on the left. I'm your host for today's session. I'm the Knowledge and Training Manager for Stratasys EMEA. And it's a pleasure to have our expert, Carolus Gedvenis, with us today. Welcome, Carolus. And Carolus, can you give us a brief summary on what we can expect from today's session?
Hello, Stefan. Good afternoon and welcome to everyone who joined this webinar session. Today we are going to talk about the first step in the FDM process, which is designing CAD model, and how the CAD design engineer can highly influence the whole process with a few modifications to his part.
Thank you. Sounds very interesting. But before we jump in, let me just try to give you a brief summary of the last session. Carolus, please jump in if I misunderstood something, but try to be short. What we learned is that with GrabCAD Print, we can use native CAD files when working and when printing files, and we always recommend to do so because then all the STL conversions are done automatically by the software and don't need to be done manually, or the settings don't need to be set, basically. Also, we talked about part orientation when 3D printing, and we mainly talked about 3 things: speed, surface quality, and strength. So for speed, we said, let's try to minimize Z height to make it as fast as possible, but also try to minimize the support material for speed and cost reasons, obviously. And the second part that we talked about was the surface quality. And here we were saying, try to have only minimally curved or angled surfaces parallel to the Z-axis. You remember the step effect on the curve that we showed within the GrabCAD Print software last week. So if you want to achieve good surface qualities with FDM, try to avoid this. And the last part we talked about here on the part orientation was strength. Meaning that the strength of the part is different across the different axes, meaning in X, Y, and Z, there is different strength or force that can be applied because FDM parts are non-isotropic. So as we learned, depending on the application that's in the part that you want to produce and create, there may be a trade-off between any of these 3 items, speed, surface quality, or strength, to get the best results. What we also learned is that slice height affects the toolpath thickness, and this, therefore, affects also the minimum wall thickness. Here we shared a short table, and that showed basically the minimum wall thickness that we do recommend for the best results. And what we also said is try to avoid varying wall thickness, try to make it one thickness across the entire wall to make it as strong and as good as possible, basically. So that's it for the summary from last week. With that, let's jump into today's topics. Carolus, over to you.
Thank you, Stefan. I hope you can see my screen.
Yes, we see your screen now.
Thank you very much. So our topics for today are self-supporting design, first of all. Then we will look into sectioning parts, assemblies, and moving parts. We will talk briefly about inserts, and in the end, I will show you one example with SolidWorks. So last session, I spoke about further steps into FDM process to get a better idea what to expect when you design the model and the operator will get your model and what he will do with your model. Today, I will talk about things to consider when designer actually creates a model and which will be printed with FDM technology. As I mentioned before, you will learn that with a few clever modifications in the beginning, the outcome can be influenced quite significantly. So let's begin with a self-supporting design. From the image, you can see three examples when we print in Z direction, so they're on the side. Green layers represent model material, orange color represents support material. So first, just a straight wall. On the first image, just a straight wall, not requiring any support structures. On the second, you see that a 45-degree angled wall is able to support itself without needing any additional structure. When the angle of the part surfaces falls below a certain degree, as you see in the third picture, which we call a self-supporting angle, then support structures underneath will be generated to prevent the surface from dripping down. So knowing this, designer can utilize self-supporting angles and reduce support material used, which directly translate to faster printing times and also saving costs of the material, especially of the support material. As you can see from the table, self-supporting angle is different across materials and also slice height. So most of the options you see have by default 40 degrees angle, 43 degrees angle, or 45 degrees angle. With exception of nylon-based materials and in a single case PC-ABS. They have self-supporting angle of 50 degrees. So based on this, we can say that using 45-degree angle should be more or less default option for your CAD model when thinking about self-supporting design.
Carolus, can you give us a brief background on why it's different for different materials?
Good question, Stefan. Well, how to put it simply, all different materials have different mechanical properties, and if we look at nylon materials, are a little bit more elastic than other materials. Therefore, when they are layered, they can drop down more easily. If we even take an example of our elastomer TPU, which can be printed on a 370 printer, the self-supporting angle will go even further up to 55 degrees of angle. So it's basically regarding different mechanical properties of the materials.
Understood. Thank you. Just a reminder to the audience, because I forgot, you're welcome to basically to ask questions anytime. Please use the question tab you find on the right. And secondly, in the end, we'll also do a question and answer session where you can raise your hand and we can then unmute you, just to make sure that everybody is aware that you can ask questions and are welcome to ask questions at any time.
Thank you, Stefan, for reminding that. So next, just a short intro on that. We have so-called chamfers, and easiest way to make your design self-supporting is using 45-degree chamfer. As you see from the both pictures, by using that you save quite a lot of time, and also you would save quite a lot of support material when printing. When we speak about holes, it is important which orientation they have. So using default options, all vertical holes would require support material, with an exception of holes which have less of 6 millimeter diameter. They can be printed without support material, but this is so-called bridging effect. So it is an horizontal extrusion between two two raised points, and as long as this horizontal extrusion is no longer than 6 millimeter, the material won't drop that drastically, and we could print those holes. But additional step from the operator preparing the print has to be done, which is removing by default generated support structures from holes using inside software. So this is something you need to take into consideration. If you are creating holes who would normally self-support, an operator needs to do an additional step to remove that support material generated. Designer can also influence the printing of holes by designing them and thinking about self-supporting angle. So here on the picture you see three variations or two variations of a simple hole. He can use a teardrop shape, which is this one, which lets to use the hole after print as intended, as normally. The second one is square, or as we call it, a diamond shape from diamond shape form. It can be used when the hole will be drilled afterwards. It has a better guidance than a teardrop shape and needs to be undersized by about 10% for drilling later. So let's talk a little bit about the tolerances. In this case, we have X and Y plane, which means we are printing horizontal holes, and so you have so-called seam on the inner surface of the hole, which usually forms after toolpaths ends the movement to close it. Normally, it's not an issue, and the hole size stays the same except of the tiny bump. But if you absolutely need the perfect hole, it is recommended to drill it after reinforcing it with additional contours, which I will talk about on the last webinar session. So make sure you stay and register for the next session. Looking at the vertical holes, you may remember from the first part, we have a so-called stair effect, which depending on the slice height might change the position of your hole by a tiny bit. And therefore, again, if you're looking for absolutely perfect holes, I would recommend you to drill them after the print. And the recommendation is to undersize the diameter of the hole by 1.5 times of the toolpath width. And if you don't know on which slice height, which translates to toolpath width, it will be printed, you can take around 0.5 millimeters and undersize it by it. And in the end, needs to be drilled to final the dimension.
Very good, Carolus. We got one question, and that's regarding the best practicing for printing holes. If I have a choice, would I print my holes horizontally or vertically?
Well, I would say if you have a chance, normally geometry might be different, but if you have a chance to influence where the holes will be positioned or how they would be printed, I would recommend, from my personal experience, to print them horizontally. Of course, you will still have the tiny bump, tiny seam, but you don't need to think about support inside the holes when they are printed vertically, and operator does not need to do additional steps in order to remove support if those holes are, have the diameter less than 6 millimeters, and it will be a little bit easier. So horizontal position or printing it in XY plane, I would recommend to have those holes if possible.
Okay, so basically also when we, thank you, and when we print vertically, your advice is to use the diamond instead of a smaller diameter hole when drilling after, right?
Exactly, yes. So you will have a better guidance with the diamond shape, and you can drill it through as easily.
Perfect, thank you.
You're welcome. So our next topic is about part sectioning, and you see we have this simple example part on the left side, and let's separate this part in two, like this. using pin for connecting them later. This part, as it will be printed as it is, and I would like to ask the audience which of the following criteria will be improved by separating parts. So if you were participating or looked recording from the last part, we spoke about orientation and what it affects. So thinking about this, if you can guess which of the following criteria will be improved by separating these parts into two. Will it be strength, print speed, costs, surface quality? So you can have multiple answers on this and just tell me what do you think which criteria will be affected or improved when printing separately. Stefan, if you can start the poll, and I would like to see the answers from the audience.
Yes, I will just launch the poll now. Please select whatever you think. It's supposed to be a multiple choice, but I'm seeing it's a select one. So just select the one that you think is mainly improved by sectioning the part. If you are in full screen mode, please leave the full screen mode in order to be able to click. So let's give it a few more seconds. And okay, we got some good participation. Thank you. And let's close it down and share the results. So most of you are saying print speed, some are saying costs and surface quality, and strength is only at about 5%. Carolus, can you tell us what's correct?
Yes, sure. I can. Thank you very much. Right, so many of you guessed correctly. Unfortunately, it was a single choice answer, should be multiple choice answer, but let's look at the first consideration, the strength. So in the left image or in the left part and separating them, we will be still printing into the same direction. And as you remember from the first webinar part, that printing into certain directions would only change the strengthness of the part. So this wouldn't be changed at all, I would say. So we can count that out. What about printing speed? Of course, printing speed, as you remember from the first session, when we print flat as possible, and we don't have any support structures in between, like we would have support structures here, the printing time is faster. So the first part on the left would be printed 2 hours 10 minutes, and the second part on the right would be printed just 1 hour and 20 minutes, which translates to around 33% of the time saving. Regarding the costs, as I mentioned just before, we won't need to print any support structures, which automatically translates to using less material. And for the first part, it would be somewhere around roughly 20 euros. For second part, roughly around 60 euros just for the material, without considering any time. And it translates to 20%. Regarding the surface quality, because we are again looking at this orientation, I wouldn't say that it would change much. It would be better when printing this time the surface quality, like this, we would have a top quality a little bit better. When printing like this, surface quality of the inner parts would be a little bit better, but it's basically a minor change. All right. So let's ask a question: why to section the parts at all? Firstly, of course, you may have a very big part which would require a big and expensive printer, and if you only have a certain build volume, you would like to section them, separate them, and print in a smaller volume printer. Second, as you saw from this first example, reducing print time, so cutting in half in the same amount, it will translate to reducing the amount of support material needed. Then we can improve strength. Given in the example, we would print the part in different orientation. In some cases, the strength might be improved too. And we can also preserve fragile features or details if we, for example, would need to post-process a part later on, so they may be damaged in post-processing if using some automatic options as tumbler or similar things. So how to do that? Basically, it's quite easy. You need to choose a good location to cut the model, somewhere with a good access for later post-processing. Of course, do not cut the part straight. You can use different joint types to increase the surface area for bonding, and you also need to think about a small clearance between those joints. It needs to be added to make space for glue. And there are actually different methods we can bond parts together again, depending on material type and bond strengthness we need. We will speak about additional methods later on in this session. Most popular are using super glue or epoxy if we do not change our model too drastically. So here you can see there are three most popular joint types are mortise, dovetail, and half-lap joints. You can also use a combination of those joints to increase bond strengthness even further. If you have to use fillets, then the radius of 1 millimeter should be added if you are using something like this in this image here. And also you can use pins to help positioning the parts for bonding to align them better. So let's look more closely into the time-saving aspect when sectioning our parts. On the left, we see a fixture to hold the back part, where you see metal fixators, which are not printing. They're just something out of the shelf. On the right, we see the same fixture, but sectioned and printing using FDM design rules. So some of the parts you see on the right side have been replaced by metal parts, which can be bought out of the shelf. For example, like bottom plate or aluminum rods for the handles and the screws to put everything into the place. Well, printing bottom plate alone would take almost 9 hours and require around 600 cubic centimeters of materials, meaning it would cost around 150 to 200 euros, roughly speaking. And I'm sure you can find something out of the shell to buy for much less of the price. So let's see in the end what we got by just simply sectioning the parts, printing them separately. First image, printing all together, 33 hours, 39 minutes. And the second, only 10 hours and 30 minutes. I'm not even speaking about a huge amount of material saved by using some different parts on that. And in the end, I can say that, of course, we can print anything, or almost anything, but it doesn't mean we should do that all the time. If we have an option, if the part is very big, we should section it if possible to have a time advantage and save some material. Moving further, if such large geometries absolutely needs to be printed and you have no other option to assemble it somehow differently, we can take this example. So in this case, time and cost savings were not done by sectioning part, but simply by removing unnecessary surfaces and also making the part lighter. Unlike with traditional manufacturing methods, we also have a higher design freedom to manufacture complex geometries, and this is advantage that should be used whenever possible. So you see on the left side, build design, build time 14 plus hours, optimized design only 4 hours, and translates to 70% time savings and 75% of cost reduction, which is quite huge.
Carolus, quick question, because I assume that this heavily depends on the application, because if I now compare these two parts, that I see the original design and the optimized design, I guess in terms of part strength, they behave a bit differently. But depending on what you want to do, and this I understand is a test fixture, the optimized design is good enough, right?
Exactly. Thank you for this comment. Exactly. So if you have some fixtures, jigs, which should only be fixated by a certain geometry or at certain places, and you don't need that part to be performing or have a mechanical strength that high, you could reduce. So exactly, Stefan. It depends on application. If you see the opportunity to reduce the material and the weight, you might do that. For example, I can take an example. If we construct a grip for a robot, and if it has to have a certain mechanical strength and we can make it a little bit lighter, that means we can even use a less costing robot to take that grip, because it would be lighter, or the robot could move a little bit faster. So just as an example, yes, it depends on application.
Okay, thanks.
Good. So our next topic is assemblies and moving parts. So making out the most out of soluble support structures with some of our materials. We can also print those moving parts in assemblies. Although consideration regarding clearances, where the soluble support structure will go, also needs to be taken. Moving parts can also be printed as assembly, for example. And as an example, we take this part on the right side and just make a cut along Z-plane, showed in blue color. First, we have a horizontal and vertical clearance, which lets our parts to move. Vertical clearance is where the support material is marked here in red, and depends on the slice height we use to print the part. And horizontal clearance without support material is marked yellow here in this example. So recommendation is that on vertical clearances where the support material will go, we should have a 2-layer or a high clearance, depending on how tight we want our part to move. In areas without support or horizontal clearances, we usually have around 0.3 millimeters or a little bit more. Same principle should be taken disregarding the orientation. If you see the similar, just we cut in the different direction, there you see the same clearances. So the vertical clearance where we have support is a little bit higher in this case, and the horizontal clear area is a little bit less. So recommended vertical clearance again in this case is 2 or more layers, and the areas without support is 0.3 or more. Next, we have a sliding clearance, and if you have an assembly where parts need to slide to each other, consider adding clearances as well. In this case, we can use a bit tighter clearances for the part not to be loose when closed, and in this case, you could add a clearance of 0.2 millimeters, and again a 0.2 millimeter clearance on the inner side, or to close the gap without a visible to close the part without a visible gap. If possible, you need to print them separate so they won't fuse to each other when printed so closely to each other. Clips might also belong to assemblies. However, they have to be printed in a certain position for the best strength, if you remember from the first part of this webinar. And again, in this case, I would like to ask the audience if they remember the first session and tell me which orientation will be best to print the clip in. Stefan, if you can help me with a poll.
Yes, absolutely. Please have a look at the picture and either choose 1, 2, or 3, the orientation in the poll. Again, if you're in full screen mode, please get out of the full screen mode in order to be able to click. I'm gonna launch the poll now and just tell us which orientation is the best to print this clip. Very good. Let's give it a few more seconds. We already got quite some good results. Perfect. And let's close the poll and share the results. So I see 89% of you are saying that number 2 is correct. I would have chosen number 2 also. Carolus, what's correct?
Exactly. So we can rule out the number 1. If you remember from the first session, each and every layer would be considered as a weak spot. Number 2 is correct. We have those layer lines, and if you remember the first session, the contour around the clip is going around through the whole part, which means we have a better strength there. And the third is something in between. It's not optional. We could print like this in the worst case scenario. So as a next part on this webinar, we have inserts, and this is where we can combine printing and out-of-the-shell inserts to use them if we need to tightly assemble our design later. For example, we can design an open slot to insert a nut after the printing, as you see in the picture on the left. However, due to shrinkage of the material after layering, after the printing, we cannot use standard values. Standard DIN values do not apply here. So as a simple rule, adding a 0.1 millimeter clearance is usually enough to design those slots. When using horizontal position, it is only possible to fasten the nut in one direction, as you see here. So it would be possible to fasten it from the below. Vertical can be used in both direction, and this fastening is quite strong, but may limit the geometry if you need to have something on top. This would probably apply to all open slots in all positions. And we can even have the diagonal position of the nut, but it doesn't offer a very good fastening strength. Nuts can also be inserted during print. It would give a better fastening strength than the previous option, but can be more work for operator, or it will be more work for operator. So he needs to use his inside software to remove the support material, or what you can do to help the operator and also save a little bit time in the process, you can add self-supporting angles into the slot if possible. So using hexagonal nuts in the horizontal position, alongside like this, using it in horizontal position will require the operator to remove support material from here, these places. But you can, if possible, make a self-supporting angle right here and save operator a little bit more time by removing those support structures. You can, using hexagonal nuts in vertical position, we have a only 30-degree angle when placed that nut on the edge. So angle for self-support should be increased. And also we would have in this case the horizontal or the vertical hole where you should consider printing, for example, teardrop shape or diamond shape and drill them afterwards. You can also use nuts diagonally, and in this case it's actually possible to adjust the angle to be self-supporting, and it could be much easier option than others, but of course it also depends on your geometry, what you want to achieve. Apart from nuts, we can use different styles of inserts after printing our model. For example, threaded insert on the left. Inserting it post-print is something similar to screwing screwing a wood screw into a plank. Another option is using heat inserts, which is on the right picture. It is easier to insert, but requires to have something like soldering iron or a similar tool to heat the insert. You also have to pay attention not to overheat the insert, as material can melt and deform itself. These inserts are quite a good option if you want to avoid designing slots for nuts. Just simply put a hole according to the manufacturing's data sheet, and then after the print, the insert can be put in the model. They also work quite well with all FDM materials.
Carolus, we got a couple of questions. One is regarding the inserts. If we can use these heat inserts also with our stiff and heat resistant materials, for example, like Nylon 12 carbon filled or Ultem 1010, for example.
Absolutely, we can use those. However, if you know those materials have a quite high thermal resistance, so it will be a little bit harder to push them in. The material would not melt that easily as let's say ASA, ABS, or other lower temperature materials. It's absolutely possible, but you need to use a little bit more force to put them in.
Okay, thank you. And then we got another question from the audience. It's how can you insert a pause during the printing in order to put the nut inside the part?
That's a very good question. Actually, I'm planning to show this on our third session when we go into the example of GrabCAD print, and I will show you how to insert a pause. It's just a two-click thing, and it's quite easy. So you need to use you can use Inside software or GrabCAD print software, and there is a menu after you slice a part. Put the Z pose inside, and the printer will pause on that layer, leaving opened the part where you can insert. You open the door of the printer, you insert for example, a nut, close the door, and continue the print. And I will show you that on the last session.
Perfect. Looking forward to it. Thanks, Carolus. That's it for now.
Thank you for the question. All right, so for the last part of this session, we will summarize most of the things we learned today through my demo with SolidWorks. But first, if you remember this part from the first session, I would like to modify the part a little bit more, and it should look like something like this. Just an example, we added a couple of more features. And what I would like to do again is to ask audience to briefly look at the part here and try to guess how many features can be improved using some of the rules we learned today. Some of the rules we actually learned today, not the last session. How many of those features added into this part can be improved? And the question is 25, 0, the part is perfect, we can print it, or 16. Stefan, if you can help me with the poll.
Yes, I will launch the poll now. You can see the numbers now. 0, 25, 16. Please bear in mind like things like the self-supporting design, the holes, what we learned about today. So it's just a guess. Let's give it a few more seconds. We'll look at that part afterwards. And here we go. Let's finish it and share the results. Almost 3/4 or more than 3/4, 77% are saying 16, 17% are saying 25, and 6% are saying 0. It's already perfect. Carolus,
right.
Can you please enlighten us?
That's interesting. I won't share the answer with you just now, but what I will do, I will just go into the SolidWorks and we'll look at the part ourselves. So I won't be doing all the changes manually. I will use something so-called configurations, which will not take as much time as normally, but basically we will take this part from the last session, and as you see or remember from last session, we have this nice surface which tells us that we would like to have this surface printed with a good quality. And if you remember from last session, we have to print this part like this. Yes, basically laid on this bottom platform. So we do the modification. You see we open up the space here. We added a couple of holes, vertical holes, horizontal holes. We added some hole nests here and there, and let's see what we can do. So first, if we look at this part, which should be printed like this, we see those overhangs like here on the right and left side. As you remember from the first short slide, chamfers can make your design self-supporting very easily. So what we can do is just put a couple of chamfers here and there, and it would be self-supported. Next, what we can look into, you remember the holes. These holes would require some support structures printed in between. Let's say that we have an opportunity to drill them later and we can modify it. So what we do is basically change those holes to diamond shape, undersize them a little bit, and we say that we will drill them afterwards. Next, what we see is those hole nests here on the left and right side, and here underneath we also have an overhang which would require some support materials. So what we can do, again, we can use a simple chamfer of 45 degrees to make this nest self-supporting. Again, we have those vertical hole nest chamfers, right? And especially in this part here underneath, we would again have some support materials, which we would like to avoid. So what we do, again, we can use chamfer. Vertical holes, nest chamfers. For some reason, they didn't apply. But similar as with the horizontal, these here we can use a 45 degrees chamfers. With the holes itself, inside we will have some support material, and we can change it. Oh, now it's applied. Okay, so we can change it to the teardrop shape to use them even without needing to drill afterwards. And what we can do additionally here, let's say we would like to fix this part somewhere on the wall or to the different part right here on the back side, we can use nuts to have this stronger fixation. We design some slots for those, which can in this case those nuts can be inserted after the print and fastened from behind. So these are basic changes what we can do with the part to have it printed better. But we did this. Let's actually look if it gave us any results. So for those who guessed that the number of features can be changed are 16, we're quite right. So we changed the part to this, and actually we did the 16 changes if counting every hole. But one thing we haven't done, what I spoke today, we haven't done sectioning of this part or removing any unnecessary material. As you remember, I said that these considerations can be better applied to the larger parts, which this part is not very large. However, we need to see if it was really worth to do those changes. So for the part on the left, you see that printing time is 4 hours 54 minutes. And on the right side, you see that printing time is only 2 hours and 57 minutes. So we saved quite a lot of time and quite a lot of support material. To be exact, our savings are 40% of the time and 20% of the costs probably translate using less support material. This hasn't been taken into consideration, that the additional work for the operator or the reserves time for the printer. So these are only material costs. So in the end, as a summary, I would say that it's best to search for any possible self-supporting angle, and you saw that you can really save a lot of time and costs. When sectioning the parts, you can improve printing time, strength in some areas if you print them in different orientation, and you can also preserve some smaller features that would probably be destroyed in some automatic post-processing. When you are printing moving parts or having assembly, consider using clearances for those parts not to fuse into each other and be able to move later on. And by using different kinds of inserts, you can improve assembly strength quite a lot. So that's for today. For the next session, which we'll have on Monday, we will speak about the infill, variable density parts. We'll speak a little bit about post-processing, texturing, or the FDM parts. And again, I will show you an example with the GrabGet print where someone asked about how to insert the pose. I will show that too, and some additional things. So thank you very much for attending the session today and listening
Thank you
to
very
me.
much, Carolus. Very interesting. We still have a couple of questions, and now is the time also, please, if you have any questions, please raise your hands or type it into the question tab, and we'll address them. We have a quick question about how much should be the minimum clearance between a threaded insert and the hole. For example, if you have an M6 insert, what diameter should the hole be?
If I go back a little bit further, I mentioned, probably it's not on the side, but I mentioned that you need to use data sheet from the manufacturer on the insert. They usually write this on the data sheet itself. So different sizes holes use different, of course, different sizes of inserts. It might be because these inserts are also used not only with the FDM, with the plastics, you can use it on the wood. So we need to look at the manufacturer's data sheet.
Okay, thank you. That's clear. And then we have another quick question on how we can actually remove the support material between moving parts.
Good question. I mentioned with the introduction of the section, I think this was somewhere here. I said that moving parts can be printed, or assemblies can be printed when we are printing with materials who are using soluble support. So this means that the support printed in between those areas, like here where we have, this whole part will be put into the tank, and the support material will dissolve itself and leave an empty space.
Okay, clear. Thank you. That's it for now. In terms of questions, also a big thank you to the audience, and obviously to you, Carolus, for walking us through this topic. It's been very interesting. And again, Carolus, if you can move on to the last two slides, because basically now if you want to learn more, of course, there's one more webinar session coming next week. There you can obviously learn more about advanced FDM, but also I invite you to just go to Stratasys Academy and register to learn more. If you go into the next slide, again, this is the Design for FDM learning program that we designed. It consists of different learning items that we do have within the company, a lot of best practices, some e-learning, some tutorials and documentation to walk through. So we invite you, have a look at the Stratasys Academy. You can find the link in the handout, in the PDF handout. You can also see on the right-hand side. With that, thank you very much. We are 5 minutes over the time, but I hope that's fine. And let's hope that we see and hear all of you at the next session about advanced FDM. Thank you and goodbye.
Thank you from me, and I hope to see you at the next session. Goodbye.